Section 6.2 is real applications of the normal distribution. So section 6.1, we learned how to use the calculator and how to understand what these answers are and how to get them. And now 6.2, we're actually going to have applications of it, the usefulness part of this. So the first example that we have there, it says the reading speeds of 6th grade students is approximately normal. So anytime it says normal, you know right away it's a normal distribution with a mean speed of 125 words per minute. So that's our mean, and a standard deviation of 24 words per minute. Part A says, what is the probability that a randomly selected 6th grader will read less than 100 words per minute? And so I'm going to go ahead and draw my bell-shaped curve, my normal curve, since I know this is a normal distribution. I also know that the mean is equal to 125. So I'll put that in the middle. And this is asking for us to find the probability, so I'll put a P, that they read less than 100 words per minute. So X is less than 100 words per minute. And so for this, I'm going to put 100 on, that is to the left of 125. And since it's less than, that means we're going to be shading to the left. Now, since I'm asked to find this probability or this area, I know that I need to use normal CDF. And for normal CDF, it's lower bound, and this starts at negative infinity, or like we saw last section, it's -1e 99, comma, where does the shading stop? At 100, comma, the mean and the standard deviation, so a mean of 125, standard deviation of 24. The usefulness of this is that as a teacher or as a district, they be able to figure out the probability of this happening and be able to target those students to get them the help that they need. On your calculator, you're going to go to second, VARS, select normal CDF, and we're going to enter in our lower bound, our upper bound, and our mean and our standard deviation. Our lower bound is -1e 99, comma, our upper bound, which is 100, comma, the mean, which is 125, comma, standard deviation, which is 24. Select enter, and we get our probability. So from the calculator, rounding 4 decimal places, we get 0.1488. Part B says, what is the probability that a randomly selected 6th grade student reads more than 140 words per minute? So again, sketching this out, put your normal curve, put your mean of 125 words per minute on there, and this one says that they read more than 140 words per minute. So 140 is to the right, and since it does say more than, we're going to be shading this to the right. So these would be students that would have excelled in reading, and so maybe they want to give this to a certain percentage of students or figure out the top 2%, which would be your GATE students. And so for this, we're going to find the probability that X is greater than 140. And again, I'm using an X and not a Z because this is not standard normal. This is something that does not have a mean of 0 and a standard deviation of 1. So in order to find this probability or area, we use normal CDF. Lower bound is where the shading starts, which is 140. Upper bound, it goes on to infinity, or 1e 99, comma, the mean, 125, standard deviation, go to second, VARS, go to normal CDF, lower bound is 140, comma, 1e 99, comma, 125 for our mean and 24 for our standard deviation. Close your parenthesis, select enter, and we get our probability. From the calculator, we get 0.2660. Problem continues on, and part C says, what is the probability that a randomly selected 6th grade student reads between 120 and 130 words per minute. So again, sketching this out, I'm going to draw my normal curve, put my mean of 125 in the middle, and it says between 110 and 130. So squeeze it in the best that you can. And again, between means we're going to shade that area between those two values. So we're finding the probability that x is between 110 and 130. So in order to do this, again, that probability or the area, we use normal CDF. Lower bound for this one is going to be 110. Upper bound is 130. Mean is 125. And standard deviation is 24. Okay, on your calculator, you're going to go to normal CDF. So second, vars. Lower bound is 110. Upper bound is 130. Our mean is 125, and our standard deviation is 24. From the calculator, we get an answer of 0.3165. Part D says, would it be significantly high, we saw these words since the beginning of the semester, for a 6th grade student to read more than 200 words per minute, and then why? So more than 200 words per minute. So let's go ahead and draw our bell-shaped curve. Put our mean on at 125. It says more than 200 words per minute. So clearly 200 is very far to the right. More than means I'm going to be shading this to the right also. And so what is that probability that x is greater than 200 words per minute? So more than 200 words per minute. And if you remember significantly high, this probability would be less than 0.05 in order for it to be significantly high. And so in order to figure out this probability, we're going to go ahead and do normal CDF. Lower bound's 200. Upper bound would be that 1E99 or infinity. The mean here is 125. Standard deviation is 24. On the calculator, we're going to go to second vars, normal CDF, and lower bound is 200. Upper bound is 1E99. Mean is 125, and the standard deviation is 24. Close parenthesis and select enter. Be careful to note that there is an E in there and that we need to rewrite this in standard form. From the calculator, you get 8.89, and it's times 10 to the negative 4th. And so whenever you get that E in there, you need to express it as a standard number and not as a scientific value. And so you would move your decimal 4 times to the left, and so this would be 0.000889, which would round to 4 decimal places, 0.0009. And so this is our probability answer here. And so it was asking, would this be significantly high? And so yes, and the reason why is because the probability is really small. It's not likely to happen, and that really small cutoff that we have is less than 0.05. So yes, it is significantly high for a 6th grade student to read more than 200 words per minute. What this means is that this is very unusual. It's not very likely. You can see that probability there for a 6th grade student to read that many words per minute. So getting them involved into a GATE program or challenging them a little bit more with different types of books would be a benefit, and this is why it's important for teachers to know this or counselors to know this idea. So the example right below says the U.S. Air Force requires that pilots have a height between 64 inches and 77 inches. Heights of men are normally distributed with a mean of 68.6 inches, standard deviation of 2.8 inches. So first question here says, what percentage of men meet the height requirement? So going here and sketching our curve, our normal curve, we know that for men, that mean height is going to be 68.6. It says what percentage of men meet the height requirement? And the height requirement says it's going to be between 64 and 77 inches. So putting on 64 and then 77 inches. And I'm going to go ahead and shade this area because it does say between. And then setting this up, this says the probability that our height would be between 64 and 77 inches would equal to, and to find this probability, again, we use normal CDF. Lower bound is where that shading starts, 64, and it finishes at 77. Our mean, again, is 68.6. Standard deviation is 2.8. Close parenthesis, and then work this out. Rounding 4 decimal places, we get 0.9484. It does say what percentage, and so to do that we just move our decimal twice to the right, so it's 94.84%. So 94.84% of men meet the height requirement for the Air Force. So that means that the rest of these men, that not the 94.84%, one minus that complement, are either going to be above 77 inches or shorter than 64 inches. So part B says if the Air Force height requirements are changed to exclude only the tallest 2.5% of men and the shortest 2.5% of men, what are the new height requirements? So again, let's go ahead and draw our bell-shaped curve, our normal curve, and put our mean on, which is equal to 68.6. So it says the tallest 2.5% of men, that would be this area in the very far right tail. So this would be that 2.5%. Expressing this as a decimal, we get 0.025. I'm going to go ahead and call this one x2 since it's on the right. And then x1 would be that shortest 2.5%, which again would be written as a decimal 0.025, which I'm going to call x1. So in order to find x1 and x2, we have to go backwards since we know that probability or that area. And to do that, we use inverse norm. And so x1 is going to be the area to the left, which is going to be 0.025, comma the mean, which is 68.6, comma our standard deviation, which is 2.8. And then likewise to get x2, still using inverse norm, area to the left of x2 is all of this. And so in order to do that, we do 1 minus 0.025, or you can write it as 0.975. So the area to the left of x2 is 0.975. Mean is 68.6. Standard deviation is 2.8. So to get our x1, we're going to use inverse norm. So go second vars, inverse norm. And area to the left is going to be 0.025, comma, our mean, which is 68.6, comma, standard deviation, which is 2.8. Close parentheses, select enter, and we get that value. To get x2, same thing, so second vars, inverse norm. Area to the left is 0.975, comma, the mean, which is 68.6, and our standard deviation, which is 2.8. Close the parentheses, select enter, and we get our value for x2. For x1, we get 63.11 inches. Make sure to put your units, so that way you know it's not feet or meters or centimeters. And then 74.09 inches. So these would be new height requirements that would exclude the tallest 2.5% and exclude the shortest 2.5% of men. So right below this, it says in Chapter 4, we learned that probabilities can be used to determine whether values are significantly low or significantly high. Like we looked at earlier, that probability that we would have for both of these would be less than or equal to 0.05, meaning that it's very unlikely to happen. So right below this, we have another example. This says the University of Maryland Medical Center considers a low birth weight to be those that are less than 5.5 pounds or 2,495 grams. Birth weights are normally distributed with a mean of 3,152.0 grams and a standard deviation of 693.4 grams. Part A says if a birth weight is randomly selected, what is the probability that it's a low birth weight? And again, a low birth weight would be less than 5.5 pounds or 2,495 grams. So which units will we use? So if you look at the mean and if you look at the standard deviation, both of those are written in grams. So we are going to be using that gram amount, which is 2,495 grams. So the probability that you are low birth weight would be X is less than 2,495 grams. I'm going to go ahead and draw my bell-shaped curve or my normal curve, my normal distribution over here on the right. The mean is 3,152.0, and a low birth weight is going to be anything less than 2,495, which would be over here to the left. Less than, I'm going to go and shade to the left. In order to find the probability of this or the area, I'm going to go ahead and use normal CDF. With normal CDF, lower bound here would be negative 1e 99. Upper bound would be that 2,495. Mean is 3,152. And then our standard deviation for this problem is 693.4. And again, those are all expressed in grams. So from the calculator, rounding 4 decimal places, we get 0.1717. Part B says find the weights considered to be significantly low using the criteria of birth weights having a probability of 0.05% or less. So in order to do this, I'm going to go ahead and draw my bell-shaped curve so we get an understanding of what's going on. So here's our normal curve. That mean is 3,152. Low birth weights would be those babies, those infants that are super small. So I'm going to go ahead and put that line over here and put an X. And it's going to be less than this, and that little area that we shaded here is going to be 0.05, which is, again, was that cutoff for significantly low. Probabilities less than this. So in order to find X and go backwards, we use inverse norm. Inverse norm is going to be area to the left, which is 0.05, our mean, which is 3,152, and our standard deviation, which is 693.4. Running 2 decimal places, we get 2,011.46, and we need to make sure we put in our units, which are grams. And so that's our cutoff. And so anything considered significantly low would be 2,011.46 grams or less. Part C says to compare the results from Part A to B. And so if you look at your answer from Part A, you can see that they are at the hospital considering a low birth weight to be anything less than 2,495 grams, when in fact something that's considered significantly low or very unusual would be something less than 2,011.46 grams. So we can say that birth weight and what the hospital had was what they considered to be a low birth weight is not significant. The next section is section 6.3, which is sampling distributions and estimators. We now consider the concepts of sampling distributions of a statistic. Instead of working with values from the original population, we want to focus on the values of a statistic, such as a sample proportion or a sample mean, obtained from the population. The idea is when samples of the same size are taken from the same population, the following two properties apply. The sample proportion tends to be normally distributed, and the mean of the sample proportions is the same as the population mean. So the sampling distribution of a statistic, such as a sample proportion or sample mean, is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. So the sampling distribution of a sample proportion is the distribution of a sample proportion or the distribution of the variable p hat with the samples having the same sample size n taken from the same population. Notation is going to be p for our population proportion and p hat is for our sample proportion. We'll see this same notation throughout the rest of the semester. Behavior of the sample proportion. One is that the distribution of all sample proportions tend to be approximating a normal distribution. And two, sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions p hat is equal to the population proportion p. The expected value of the sample proportions is equal to the population proportion. Also, the sampling distribution of the mean of the sample mean is the distribution of all possible sample means, or the distribution of the variable x bar, with all samples having the same sample size n taken from the same population. Again, the notation is going to kind of follow us through the rest of the semester. And we have mu is equal to the population mean and x bar is equal to that sample mean. Behavior of the sample mean. The distribution of the sample mean tends to be normally distributed. The normal distribution tends to become closer to a normal distribution as the sample size increases. And the sample mean targets the value of the population mean. The expected value of the sample mean is equal to the population mean. So taking that and kind of using that stuff into section 6.4, which is the central limit theorem. In the previous section, we saw that the sampling distribution of the sample mean tends to be a normal distribution as the sample size increases. So again, as the sample size increases, it looks more and more normal. So given any population with any distribution, it could be skewed or uniform, etc., the distribution of a sample mean x bar can be approximated by a normal distribution when the samples are large enough. And for us, large enough is going to be when n is greater than 30. The central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. If n is greater than 30, the sampling distribution of x bar can be approximated by a normal distribution. So it'll be approximated by a normal distribution. It's going to have a mean of mu and a standard deviation of sigma divided by the square root of n. The more skewed the distribution of the population is, the larger the sample is needed to invoke the central limit theorem. So right below this, you can see 4 pictures here. And you can see that as our sample size is increasing, our distribution is getting more and more normal. And you can see that normal bell-shaped curve, and then also from collecting the data, that histogram. So suppose that a simple random sample of size n is drawn from a population with mean mu and a standard deviation of sigma. The population has a normal distribution, or n is greater than 30, that's our sample has to be large enough, or it must be stated that the population has a normal distribution. Then the sampling distribution of x bar has a mean and a standard deviation that are given. So the mean of x bar is equal to, and it's mu sub x bar is equal to mu. And then the standard deviation of x bar is going to be sigma sub x bar is equal to sigma divided by n. And this is called the standard error of the mean. It says if the original population is not normally distributed and n is less than or equal to 30, then the distribution of x bar cannot be approximated well by a normal distribution, and the methods discussed above cannot be used. So right below this, there's an example. The example says, based on the test of the Chevy Cobalt, engineers have found that the miles per gallon in highway driving are normally distributed. So they tell us it's normally distributed with a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. Part A says, what is the probability that a randomly selected cobalt gets more than 34 miles to a gallon? So the probability that our cobalt gets more than 34 miles to a gallon, and this looks just like what we saw before. And so in order to do this, we use our normal CDF. And our lower bound, and if you want to sketch this out to get a better visual representation of what's going on, the mean here was equal to 32, and this was asking for 34 miles a gallon or more than 34. So shading it to the right. And so our shading starts at 34, goes on forever to the right, which is infinity, or for us is 1E99. Mean is 32, and our standard deviation is 3.5. This is the same thing that we have done before. On the calculator, we're going to go to second, VARS, normal CDF, lower bound is 34, upper bound is 1E99. Mean is 32, and our standard deviation is 3.5. Close your parentheses, select enter, and we get our probability. We get 0.2839. Now, looking at this and then also looking at part B. So B says 10 cobalts are randomly selected and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? So, looking at the difference between this, it still says exceeds, which is the same thing as more than that was up here. But what is the difference between this? There's a difference because this one says a randomly selected cobalt, part A, whereas part B says 10 cobalts are randomly selected. And then also it says, what is the probability that the mean miles per gallon, and so that word mean here was not up above in part A or what we have seen previously. So this is going to be using that idea, that central limit theorem, and so we're going to have finding the probability that the mean miles per gallon, so probability the mean miles per gallon x bar exceeds 34. So this would be done exactly the same way. Our normal CDF, it's still 34 going on to infinity, which is 1E99. However, we need to use, and I'm going to go ahead and scroll here, the mean and the standard deviation that we have listed up above. And so the mean is just mu, but our standard deviation is going to be equal to sigma divided by that square root of n. So our mean is still going to be 32, comma, our standard deviation, which is 3.5, divided by the square root of n. And n is your sample size, and it tells us right there that our sample is 10. So divide by the square root of 10, close your parenthesis. On the calculator, we're going to go to second, VARS, normal CDF. Lower bound is 34, comma, upper bound is 1E99, comma, our mean is 32. And then our sample here is 10. So typing this in, do not round, otherwise we end up with some rounding errors. You're going to type it in just as it is written. So 3.5 divided by the square root, which is second x squared, and you should have a square root symbol sitting there. And then type in 10, and then I'm going to move my arrow over so I'm not inside that radical symbol anymore, and I'm going to close my parenthesis, and I'm going to select enter to get my probability. From the calculator, we get 0.0354. Part C says 20 cobalt are randomly selected and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? Would this result be significantly high? So we will get into that in a moment. But it does say the same thing here about the miles per gallon exceeding 34 miles per gallon. But it does still say that mean miles, and this time we do have 20 cars that we're going to be surveying. So probability that our mean miles or X bar exceeds 34 using our normal CDF. And it's going to be lower bound, which would still be 34, upper bound going on forever, 1E99. The mean, which is still 32, and then standard deviation would be our sigma divided by the square root of n. So 3.5 divided by the square root of n, and for this one it's going to be the square root of 20 since that was our sample. On the calculator, we're going to go to second, vars, go down to normal CDF. Our lower bound is 34, comma, upper bound is 1E99, comma, our mean is 32, and then our standard deviation this time is taking that standard deviation that we have and dividing it by our sample, and our sample is 20. So we have 3.5 divided by the square root of 20. And again, do not round this, type it in exactly as it is. Select enter, and we get our probability. So from the calculator, we get 0.0053. It also asks if this is significantly high. And the reason why it does say significantly high is because we're dealing with greater than here. So is this significantly high? Yes. And it's significantly high because the probability of X bar being greater than 34 is equal to 0.0053, which is less than that cutoff of 0.05. So right below this, we have our rare event rule for inferential statistics. It says if under a given assumption, the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect with the assumptions, we can conclude that the assumption is probably not correct. So right below this we have another example. This says assume that cans of Coke are filled so that the actual amounts have a mean of 12 ounces, standard deviation of 0.11 ounces, and it says assume that the weight of cans of Coke are normally distributed. Part A says find the probability that a single can of Coke has at least 12.19 ounces. So again, this is going to be the probability that our single can of Coke, I'm going to call it X, is greater than or equal to 12.19 ounces. Sketching our normal distribution gives us a little visual representation here. Mean is 12. So to the right we have 12.19. And it does say has at least 12.19. So shading this to the right. So again, we would use normal CDF to find that probability. Lower bound here is going to be the 12.19, comma, infinity, or 1E99, comma, the mean, which is 12, comma, the standard deviation, and standard deviation is 0.11 ounces. On the calculator, we're going to go to second, vars, normal CDF. Lower bound is 12.19. Our upper bound is 1E99. Our mean is 12, and our standard deviation is 0.11. close your parentheses, select enter, and we get our probability. So from the calculator, we get 0.0421. Part B says the 36 cans of Coke in a data set have a mean of 12.19 ounces. Find the probability that 36 random cans of Coke have a mean of at least 12.19 ounces. So again, probability, it's a mean amount, so X bar of at least, so greater than or equal to 12.19. So again, we have 36 cans of Coke, but going to use normal CDF. Lower bound here is going to be that 12.19. Goes on forever, 1E99. Mean is still 12. Standard deviation is going to be 0.11, all divided by the square root of 36, or just 6. On the calculator, we're going to go to second, vars, normal CDF. Lower bound is 12.19, upper bound is 1E99. Our mean is 12, and then our standard deviation is going to be the 0.11 divided by our sample, which for this problem is 36, so the square root of 36. You can also type this in as just 6. Close your parentheses, select enter. From here, we get 1.8539 times 10, or e, to negative 25th. So most of the time it's going to ask you to round 4 decimal places. So if you were to move your decimal point 25 times to the left and round it 4 decimal places, you would get 0.0000. Right below this is an outline. And the outline has what happens with the shape and the center and the spread, assuming that the population is normal with a mean mu and a standard deviation given of sigma. Population is not normal with a mean mu and a standard deviation of sigma. So take a second to look at that. It's just a summary. The next section is section 6.5, assessing normality. We are going to be using this section and this idea in our individual projects for our course. So it says, in this section we present the criteria for determining whether the requirements of a normal distribution are satisfied. The criteria involves visual inspection of a histogram to see if it's roughly bell-shaped, identifying any outliers, and constructing a normal quantile plot. So first thing is a normal quantile plot, or a normal probability plot, is a graph of points x, y, where each x value is from the original set of the sample data, and each y is the corresponding z-score that is expected from the standard normal distribution. So a procedure for determining whether it is reasonable to assume that the sample data are from a population having a normal distribution. First thing is that visual inspection of a histogram, and so we want to look to see if it is roughly bell-shaped. So we want it to be roughly bell-shaped. If it's not bell-shaped, then it's obviously not normal. And then step 2, we are going to look for outliers. And the rule that we have in our textbook is that if you have any more than one outlier, it's not normal. So 0 or 1 outliers are okay. Anything more than 1 is going to be not normal. And then 3 is that normal quantile plot, which was discussed up above. And it says there that the population distribution is normal if the pattern of the points is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight pattern. So not a normal distribution would be the population is not normal if either or both of the conditions apply. The points do not lie reasonably close to a straight line on the normal quantile plot, or they show some kind of pattern, some systematic pattern that is not a straight line pattern on the normal quantile plot. The next example says a random sample of 100 adult males' blood pressure was recorded. The data then was used to create a histogram and normal quantile plot that are given below. Determine whether the data appears to be from a population with a normal distribution. Explain why or why not. So looking at our histogram, it looks roughly bell-shaped. So I'm going to put down histogram is roughly bell-shaped, which is what we want. 2 is going to be looking for outliers, and we can say that doesn't seem to be any outliers. Outliers, like we've seen before in our past chapter notes on a histogram, are usually represented by something far off here, like another bar, and we don't have anything like that on the left or the right sides of this graph, so we can say does not appear to have any outliers. But again, if we had the raw data, we can easily calculate our interquartile range using one var stats and getting Q1 and Q3, and then from there calculating those fences to determine if we have any outliers there. The next thing that we have to check is going to be looking at your normal quantile plot, which is over here on the right. And again, it says the population distribution is normal if the pattern of the points is reasonably close to a straight line. And looking at that, that does look like it. And the points do not show some systematic pattern that is not a straight line pattern. So we'll say it looks like it's a straight line. So points on normal quantile plot are close to straight line. And so from this, since we can conclude that all three of these criteria are met, that the sample data are from a population that has a normal distribution. So we are going to have to do this to test the data that you collect and to see if we can say that the sample data are from a population having a normal distribution.